Hi, my name is Hyeontae Son from Seoul National University. We present SAUM Symmetry-Aware Upsampling module for consistent point cloud completion. We address the point cloud completion, which is estimating the complete point cloud given an incomplete one. Most of the previous methods for point cloud completion share the encoder-decoder structure, where the encoder projects the raw point cloud into a low-dimensional feature vector, which is decoded back to the list of points by decoder. And most of them concentrate on the efficient decoder design using various methods such as fully connected layers, two manifold-based approaches, coarse-to-fine manner, and tree-based architecture. Despite the different choices of the decoder architecture, the outputs, which are shown in red, are usually inconsistent with the input points, which are shown in green. As you see in the examples, the local details such as sophisticated tails of airplane, chair legs, ornaments of the lamp pillar could not be fully recovered. We thought that the main reason for the problem is the limitation of the encoder-decoder architecture. The decoder regresses the output points from the condensed information within the lower feature vector, and which does not contain full local details. To keep the high frequency details, we concentrate on utilizing the local features from the encoder layers, which is a relatively unexplored approach. It is non-trivial applying conventional skip connections to the point cloud completion task. While skip connections in image domain connect the symmetric layers between the encoder and decoder to preserve hierarchical local features, in point cloud completion, the number of input and output points are usually not the same, and the feature maps of the encoder and decoder are not symmetric. As a naive approach to bypass the problem, existing works suggested to construct a coarse point cloud in the decoder network by concatenating the input and then pass it to further refinement network. But this approach directly uses the input and does not utilize the feature maps extracted from the encoder, so there is still room for improvement. We propose a simple method using a two-branch network by attaching an upsampling module. SAUM is our upsampling module, and it generates point cloud from the encoder's feature maps. The final output is a union of the point sets from the two branches of SAUM and decoder. An exemplar output of the two branches are shown in blue and red, and the union is given as green. SAUM is an abbreviation of Symmetry-Aware Upsampling module and shown in blue. Interestingly, the upsampling module can preserve the symmetric structure even if we didn't explicitly enforce the symmetry. We further explain the network architecture. This slide shows the encoder network in the blue box. We follow the conventional encoder that uses PointNet-based network. The encoder is composed of 4 shared MMP layers, and the last layer is mapped into the lower feature vector with max pooling. The encoder-decoder architecture regresses for a fixed number of points from the lower feature vector. The 4 layers of intermediate encoder features are the input to the SAUM, which upsamples the input points by ratio R. Given n points, the SAUM generates Rn points. The final output is the union of points from the two branches. Note that SAUM is independent from the decoder network, so we can attach it to any existing method with different decoder architectures. We jointly train two branches using chamfer distance as a loss function. Chamfer distance is the mean of the nearest neighbor distance of each point in the 2-point sets. It can be calculated regardless of the sizes of point sets, so we can handle the varying size of inputs without additional sampling during the training time. Recall that SAUM upsamples the point by factor of R from the multi-level features from the encoder. Specifically, SAUM consists of the point expansion modules attached to individual layers of the feature maps. Point expansion is a special case of feature expansion proposed in PUNet, published in CBPR 2018. The point expansion module upsamples the input feature map with a specific ratio, and the output of SAUM is the union of upsampled points. Point expansion consists of multiple shared MAP layers and the reshape operator. Note that the final dimension of each shared MAP is 3, so they are mapping from the input feature maps to 3-dimensional coordinates. As a result, SAUM generates upsampled points from low-level to high-level feature maps, emulating unit-like ski connections. This figure shows 4 examples of the input, outputs of the 2 branches, their union, and ground truth. Results clearly show that SAUM can utilize the symmetry of the input point cloud, such as reflective symmetry in airplane wings and rotational symmetry shown in chair legs. While the feature expansion is known to have a tendency to upsample the original points near the local region, surprisingly it can find the symmetric points in the completion task. By jointly training a 2-branch network, decoder networks are estimating the residual part of SAUM, so resulting in complementary branches. We show more completion results with various examples. Incomplete shapes are in the leftmost column, and the corresponding ground truths are in the rightmost column. The red point clouds are the results inferred from encoder-decoder networks. All networks share the same encoder, and the only difference between them is decoder architecture, of which name is written in the top row. Generated points usually suffer from the noisy and blurry shapes, and lose detailed geometry in the input point cloud. The green points are the outputs of the SAUM attached models. We write down the 2-branch models with the decoder architecture's name postfixed by a plus sign. With the aforementioned properties, our 2-branch network can generate point clouds, preserving the details, enabling the locally consistent point cloud completion. As an additional experiment, we ran self-consistency test. Basically, we demonstrate how the network can recover the original shape by using the ground truth shape as input of the network. The outputs from the decoder-only method still suffer from the blurry shape even with the perfect input shape. This result clearly shows the loss of detailed features, and it is due to the last global max pooling layer of the PointNet encoder. In contrast, our 2-branch network can keep the information of the input mainly in the SAUM, so it can boost the local consistency. We evaluated the performance of our method with 4 metrics: chamfer distance, Earth-Rubus distance, F-score, and fidelity. We colored the result bar as red for decoder-only methods and green for ours. Chamfer distance and Earth-Rubus distance compare the distance between shape completion results against the ground truth data. Our module reduces both distances in PCN and TopNet datasets. F-score measures the accuracy and completeness of the reconstruction at the same time, and the higher, the better. It is clear our module improves the F-score as shown in the upper row. For the real-world data, there is no ground truth, so we measure how the shape completion can preserve the input shape by measuring the fidelity. Fidelity is chamfer distance between input and output, and we use it for the KT dataset, and the shape fidelity is better for SAUM attached models. In summary, the results show that attaching SAUM boosts the performance of existing methods in all metrics. In conclusion, we summarize our work with 3 main points. We present 2-branch network for shape completion. SAUM is an additional branch utilizing local features and finding intrinsic symmetry, and it helps to locally consistent completion. The jointly trained decoder is complementary and can find the global structure. Thanks for watching my presentation.